Hello and welcome to Machine Learning from Data. This is lecture 10 and this is video 1. And in this lecture, we are going to talk about something that's known as the non-linear transforms. This is a very useful addition to the linear model, and we'll see how this helps us in answering certain questions that are otherwise in their original form, or at least like if we have data in its original form, it's sometimes hard to deal with. And so that's the focus of today's lecture. Let's begin with a quick recap of the linear model. Now, having talked about using the linear signal for answering different categories of questions, essentially, right? So this picture here essentially summarizes everything that we've been talking about in the previous few lectures. And this summarizes everything in terms of the credit analysis problem. For example, if in the credit analysis problem, the question that we're trying to answer is about approve or deny, then again, using the linear signal, which stays as it was, S equals W transpose X, where it's linear in X, so that's why we get the linear separator, right? So that's the basic model. And then it's linear in W, so that makes the algorithm work, because like the algorithm is picking up those W's, and so it's linear in that as well. Right? That's the goal, and that's why this linear signal is so powerful and so useful. And we saw that we can answer three large categories of problems. So the first one, as I was talking about, was the approve or deny problem. So you have the outcome as a +1 or a -1, right? So +1, sorry, and -1. In that case, the algorithm that you will use is the perceptron learning algorithm. And like based on what do you select your W's? Basically based on the classification error. And then we saw two, as I said, the algorithms that we saw were the PLA and the pocket algorithm. Pocket algorithm allowed some tolerance for error, and PLA just iteratively classified our data into +1 and -1. So that was the first. And then the second is the amount of credit. So if you're like really interested in getting your Y to be a real number, like the actual credit line, then we use something that's known as linear regression. So this was the model, and then we utilized squared error, tried to minimize that using something that's known as the pseudo-inverse algorithm. It was a very powerful algorithm because we did everything in a single step, because we could come up with that particular expression and in fact utilize that. And then we saw some variants of that, like using regression for classification, and how can we like improvise on the pocket algorithm using this knowledge that we have from regression and so on, right? So that was the second category of problems. And then finally, the third category of problems, which is also equally important, is the probability of default. So if you're not interested in exact approve or deny, and rather we are interested in getting the probability of somebody defaulting or not, then we used the model that's used is logistic regression. And maybe I have it at the wrong place. These are all the models, to be honest. And these are the algorithms, right? So this is the algorithm, this is the algorithm, this is the algorithm. Okay, anyways. So the model was logistic regression, and what the algorithm was gradient descent, and we used the basis to kind of get the weights in that was cross entropy error. We derived that, and then we using gradient descent and also stochastic gradient descent, we could come up with the better, like more efficient way of getting those weights that we were interested in, right? So, but the basis was cross entropy error. Now, we saw that linear model is powerful, and in fact, so much so that we can say that we can solve most of the machine learning problems using the linear model, right? Because like we know these three major categories, and we can use any one of those and solve the problem. Now, sometimes um, there are certain limitations with the linear model, and let's look at this picture to better understand that. Now, if we look at this one, linear with outliers, this picture, you can tell that, oh, okay, the data is not perfectly linearly separable, right? We have these misclassified points, but then going back to the pocket algorithm, we know that we can allow for some sort of tolerance for errors. And so, yeah, I mean, I feel PLA would do justice to this. And PLA, I mean, pocket algorithm that builds on PLA should do justice on this, that we are allowing some errors, but yeah, we are getting a decent classifier in the form of this line, right? So this separability, I would say we have looked at this, like data with few outliers, and we kind of like this because I can directly use some of my known algorithms on this. Okay, let's look at the picture on the right hand side, right? And here, if I kind of use my pocket algorithm, I cannot say for sure that I can get like some kind of linear separability. So this is a different kind of like non-separability, I would say, right? There is something fundamentally different here. I cannot really attribute it to some outliers there. Okay. Now, we tend to like the linear model a lot, right? We've spent 2 to 3 lectures just like talking about the linear model. And not just that, because of the flexibility it offers. We've seen that, right? Now, we will again today use the linear model to solve a problem like this, where the data is essentially non-linear, but we need something that we can build on this data and then utilize the linear model again, right? So we'll do that today, and that technique is known as the non-linear feature transform. So that's exactly what we are going to use. And let me write it down here. Today what we are going to use, it's a technique called non-linear feature transform. And I'm just going to show you on what kind of problems should we be using that non-linear feature transform. Okay, so let's consider the credit limit problem again, because like we are pretty familiar with that. So let's use that, right? So credit limit problem, right? And let's say we are looking at 2 features. So the 2 features are the income of the person. So income, let's say I'm denoting it by I, and years in residence is, let's say I'm denoting it by Y, this feature. And there are a few things I know about this problem. For example, it makes sense that this years in residence feature would affect a person's credit since it's like correlated with stability, right? But then it is less likely that the credit limit would grow linearly with the number of years in residence. So basically what I'm saying is that if the years of residence are less than 1, let's say this is like 1, 2, and like 3, 4, 5, and so on. So anything less than 1, right? I would say that this would like affect the credit limit negatively, right? Somewhere here. And then most likely whatever comes in here should be like the outcome should be negative. And anything above 5, I don't know, it doesn't really matter after that. So the anything above 5 would affect the credit limit like positively, right? So maybe, I mean, I don't know, the like the Y and sorry here, and then let's say this is going to be a straight line, and then beyond that, I don't know. I mean, it's going to stay pretty stable like after 4 or 5 years or something like that. So there exists these threshold below which like maybe I cannot say that something like this, but yeah, there is like this region. I don't care about, you know, the months and all of that. Let me just like remove this thing here. Yeah. So for problems like these, basically what I'm saying is that if the input, if like xi is the input variable that measures like the years in residence, or like in our case it's y, so let's call that y, then there are 2 non-linear features that can be derived from it. So basically what we're saying is that there's going to be this like feature where like my y is less than 1, and also when my y is, and this is the indicator, and my y is greater than 5, this would allow some kind of non-linearity to reflect in the credit limit, right? It wouldn't be like really saying that as you know, the years of residence increase, like even if you have a lower income, there isn't like a linear sort of way of like separating these 2 regions. Let's say this region was when we are like +1, less likely to go wrong, and this is like the -1 region, right? So this is what exactly. So linear model is not right here. Like let's say this is the line for separation, and these are like the two gray areas. This one and this one. This is precisely what I'm trying to say. This is not exactly linear, right? Because like this year's feature is not right in some way when we collected this data. So we should include this kind of saturation in my features, right? So this is something that's known as saturation that happened here and like in both these cases. Some saturation happened and I should be able to take care of that. So how should I do that? Well, one way is that instead of like trying to go after how to I would say represent this, right? How to use this as it is, we can transform it. So what does that mean? So that means is that I can take like any feature, let's say take this feature years in residence. So take feature Y, which is years in residence, and then do some transformation, apply some function on it, right? And maybe create a new feature. And if the relationship between the new feature and the old feature, which is like Y and Z, is somewhat something like this, where you have like this, and then this is linear, and then this is this. So basically, based on this threshold, right? I know many Y values will come to the same Z value, right? So then, for example, when Y goes above a certain threshold, like this is my threshold, when Y goes above that, then Z is just like 1 point. Z is just high, right? And when Y is below a threshold, then Z is just low. And then that's the same point, right? So this is the kind of thing that we're looking at instead of like going after including all these parts in my Y and then just like making it complex unnecessarily. So why is this like useful? That's the big question, right? Why is this useful? Well, this is useful because we are going to get rid of that non-linearity. What will happen is, let's say this was the income, this is my new Z feature, and everything would be something like this, like high values and low values. And so it will become easier to separate this, which wasn't like the case here, right? It was like these two thresholds were kind of introducing some kind of, I don't know, this is hard to describe kind of a function, right? But here, this is like a linear function. And so between high and low, everything is linear. And so I'm good, right? So now I have a linear separator. And now I can easily apply all my prior knowledge here because we know a lot about the linear signal. We know about a lot about the linear separator and all of that. Okay. So now we move on to the mechanics of this nonlinear transform. Of course, the tricky part here is that, right, I'm talking about the data, I'm looking at the data and saying, okay, this thing fits better than that. But remember, you cannot look at the data before you decide whether or not to apply the feature transform. So that still holds because my theory is going to fall apart. The relationship that we build between E in and E out and other things is going to fall apart. So I have to remember that. And so let me write it down first of all. So we're talking about the mechanics of nonlinear transform. Linear transform. And how do things work here? Okay, so linear model is not good for many problems. And so let's say this is one of those problems where we have like two features, x1 and x2. And this is the axis. So let's say this is like 0 in the middle somewhere. Okay, this is 0. And then let's say I have these data points. Let's say this is one category. By the way, that 0 looks like one of these points. Well, that's fine. And then I have this other category, which looks something like this. Okay. Okay, that's it. I think that's good enough. And so I have this, and of course, linear model cannot kind of classify this, right? And so, as I said, the question arises like, we cannot look at the data before we decide whether or not to apply the transform. Ideally speaking, yes, that still holds, but how we build like and how we decide to apply feature transform is, for example, here I know that this thing happens, right? I know that there is this phenomena that might lead to answers that are not really good for my linear model. I know that the saturation happens in this credit card problem. Similar to that, we saw in the classification of handwritten digits, where intensity and symmetry features were the important ones, and I couldn't use like all the features that were given to me. So depending on the problem itself, I have to define, like I have to decide for this transformation, right? And so that's the key here. Well, let's move on. How will the actual nonlinear transform work? So what do we have in my input? What do I have in my input? My input looks something like this. My x, let's call it x space, because we are going to move everything to a new space, and that is something that I'm going to call a z space, so that we can differentiate. Okay, so this is 1, x1, x2 augmented. We know why, so I'm not going into that. And as I said, I have to apply some transformation on it, and that transformation I'm going to call or denote by the function phi. Right, so this is what we're going to call it, phi. And so the transformed new feature space, as I said, I'll be denoting it by z, and that will look something like this: 1, z1, z2. Okay, so what is this z1 and z2? It's nothing but this phi, which the function that we decided is going to transform my x1 to z1. So this is going to be phi, maybe I can say phi x1, right? And phi x2, whatever that function is, and that corresponds to my z1 and z2. Okay, so just by looking at this data here, this x space here, like generally speaking, right, I can tell like that there is this there is a relationship between each of these points. There is this circle, I would say, that can separate my data into two parts, right? So maybe I can have something like a x1 squared plus x2 squared equals like something here. Let's say it's like 0.5. Let's assume it's 0.5, right? Let's say we know this, like this is my non-linear hypothesis in my original space. It is separating the data perfectly, but because like working with non-linear functions is not as convenient, and we want to, sorry, this is squared, and we want to have a linear hypothesis, right? So we will apply some kind of a transformation on this. So in particular, in this case, what's going to happen is just by looking at it, I can tell that the points that are really close to my origin, this 0, right? Um, well, the points that are really close here, and if I have applied this like feature transform here, which is like phi x1 using this something in my like input space, so I can say that like there are certain points that are really close, could be one category, and that are really away could be another, right? So we can view this hypothesis as a linear one after applying this transformation. So in particular, what we are saying is my z sub 0, right? Z sub 0 is still going to be 1. I don't do any transformation here. But my z1 is nothing but my x1 squared. And my z2 is nothing but my x2 squared. Now, if I apply this transformation, I can tell that the points that are close to the origin in the original space have a small value of like z1 and z2, and those that are far away will have a large value. So what does that mean, right? Let's look at create a picture and then try to do the mapping, right? So let's try doing that here. So let's say this is my transformed space, and as I said, points that are close to the origin, like the ones that lie in the circle, must have like a small z1 and z2 values, and that's why they lie here, right? And then the features that are away from the origin, they must lie somewhere here. Sorry, so let me maintain the cross. Okay, so now in this new space, which we are going to call z space, because this is my new transformed space, the mapping of the original points and the new transformed points, depending on whatever function I decided to apply on those points, looks something like this. And this is good news for us because I can easily apply a linear separator here, right? So in the new space, we can separate it by a line. right? So this is the whole idea. Let me summarize it. The original data set was not linearly separable, and it was separable by a circle. But we transformed it using some convenient mathematical function into the new Z space. And then what's going on is like every point in my input space is going to map to a point in my Z space. And it could be that there is a low overlap. That's fine, right? That is allowed. So if we plot, so what we did here was we plotted that new feature space here, which in our case was this was the original, and this is what we came up with. So essentially what we came up with was, let me write it, then phi of, what did we call that, x, right, is nothing but 1 and then x1 squared, x2 squared, right? So basically the transform phi takes us from x to z, and this is known as the feature transform. Okay. Also, like one word of caution. Now, in general, some points in the z space may not be valid transforms of any x, and there can be multiple points in x that can be transformed to the same z, like we saw. So it totally depends on what nonlinear transform phi we are using. Okay, so the usefulness is to get this like straight line. For example, in this case, I can use PLA, right, and apply to this transform data, right? And now the hypotheses that I'm going to get, and I'm denoting it by tilde, because now this is my new transformed space. It doesn't really exist in terms of the data, and I just created it. So this is my hypotheses, right? Because this is what we are after, and because I'm applying this linear classifier here, so this is going to be the sign W tilde transpose Z. Now, like generally speaking, all of this transformation is behind the scenes, meaning if you're working for a client who wants to know answers to this like credit line problem, you need to give them answers in the original space, right? So there is like, when the new test point comes in, it will come in in this space, right? And not in this one. And so how am I going to answer that? Well, the high level idea is take that point, right? So let me write it down. So how this is going to happen is take that test point, right? And then apply phi, which is my feature transform, apply phi on that point, right? And so I'm going to get some value for that in my Z space. So get value in Z space, right? And so that new value is going to be phi of like whatever, let's say that new point is some x of I, so I'm going to get some value for that. And so what's going on is, like if you look at it again, and if you remember, this was my x and this is my Z space, right? And let's say I have a linear separator. What's going on here is that I have these points here, and so I have like effectively created a circle here, right? And so if my test point, my new test point comes in here, let's say I'm drawing it by a square, ideally speaking, and not ideally speaking, because we have chosen our feature transform to be such that this is going to lie somewhere in this region, right? And so like all the points, like in effect, we have implemented a boundary between the plus and the minus regions, even in our original space, which is non-linear. But this is an effective boundary because we somehow are trying to find the answers using the easier version of this, that is the linear model, right? But we are just using the linear model behind closed doors, right? So this kind of um, tells us that we are trying to exploit the power of the linear model because we have all the algorithms, we know the model formation, we know the errors and all of that. And so that's why we are doing all this, right? Because you might ask, why are we doing all that, right? And so, and this will become even better, like more clear when we talk about E in and E in and E out. But for now, like whatever point comes in is going to be here. And then if a point comes in here, right, this would be mapped to this. And so we can answer whether it lies in this versus that, right? So let's try to kind of summarize this feature transform, right? And basically also try to get some perspective on what our final hypothesis is going to be. Because what we just said here, this G tilde of Z is not a final hypothesis. Because as I said, if you're working on some problem and then your client wants answer for a new test point, you cannot give them answers in terms of the z space. So you have to come back to your x space. And so what is that hypothesis that is going to be? So let's look at that. And in fact, oops, I think I can write it here only. Okay, I'm running out of slides, so that's fine. So my x space is something like this, 1 and then x1 and so on. Let's say it's d-dimensional, right? And then my z space, and let me write it here. And so by the way, we have, oops, we have this thing already there, or let me see. Can we add slides here? Let me add some slides here because I think we've run out of space and I just don't want to lose the flow. Okay, let's do this. Okay, so I just want to summarize like what's going on in this entire feature transform thing, right? Basically, our final hypothesis is going to be, as I said, in the x space, and this is going to be the g tilde, and that is going to be whatever the feature transform we used, which is nothing but the sine of my W transpose P of X, if you think about it. And then, of course, this like we will just like discuss in a minute what this W is, right? Because this is not really making a lot of sense, whether this W is in my Z space or in my X space. So let's talk about the input. The input for my, and let me separate this X and Z and draw a line. So my input would look something like this, 1, x1, and so on, let's say d-dimensional. And in this case, the input is phi of x, which is equal to 1, z1, and so on to z of d, which is nothing but, if you go back, phi x1, and so on, phi xd. Right, so that's that. And in terms of the data, right, what's going on in terms of the data? So we have x1, x2, and so on. Let's say, I don't know, whatever, xn. And then I have my outcomes, y1, y2, yn. Here, the data becomes the z points, z1, z2, and so on to zn. But my y's don't change because I'm still classifying, if you remember, I'm still classifying points into +1, -1, which I was doing here as well, right? And so my y's stay the same, y1, y2, and so on, right? And so we implement the linear model in Z space, right? Which means that my hypothesis is h of Z, right? Which is going to find some weights in the Z space. And so I'm going to denote them by the tilde again because I'm still in the Z space. And this is what I'm finding essentially, right? So I have like these weights, let's denote them by W linear tilde, which is nothing but this vector W0 and so on up to WD tilde, of course, right? So there's still D plus 1 dimensions. And then finally we arrive at that G of Z equals sine W linear transpose Z, right? So we get the sign here, right? And then what happens to the weights here? So there are no weights here because I did not run my algorithm here, right? So there won't be any weights here. But I need a final hypothesis because remember, that's the answer that I need to give to my client. So I need a g of x in my x space, which is nothing but my g tilde, not tilde, and then phi of x, which is, then I'm just like substituting things, which is essentially telling me the sign of, because now we have this, right? So I'm utilizing that, right? Every time I'm getting something in x, I'm utilizing that to get the sign. That's all I'm doing, right? I don't have to run the algorithm in my x space. That's the thing. Okay, so that kind of summarizes the feature transform, the basics of the feature transform. We managed to get E in close to 0 in this case, so we are getting E in close to 0. In the next video, let us talk about the error a little more and also talk a little bit about the relationship between E in and E out.